pleasure to introduce Professor Hamsa Balakrishnan. She's an associate professor in the Aeronautics and Astronautics department at MIT, where she's also the associate department chair, department head. She's a co-founder and chief scientist of a startup called Lumo, which is a transportation-based startup in Boston area. She works primarily in optimization and control applied to air transport domains, and she has received many awards, primarily NSF Career Award, the inaugural CNA Award, the Donald P. Ekman Award. As you can see, I cannot remember all of them from the top of my head, so I'm using an A, and she has received multiple Best Paper Awards. So with that, I want to welcome her, and we'll be happy to have her talk.
Thank you very much. Thank you for the invitation. It's a pleasure to be here. I'm going to be talking about something that some of my research today that I think embodies a lot of what this institute tries to do and works on and does very well, but in the context of air transportation and in particular delays in air traffic networks. So I think, we're coming up on Thanksgiving in a couple of weeks, and a lot of people are going to be flying. So if you're delayed, don't blame me. So just in terms of a broad overview of the system, since this is a slightly more general audience, it's hard to argue with the statement that air travel now drives global travel and commerce. Commercial passenger enplanements. So this is somebody getting on board a commercial airliner to take a trip somewhere. There's about a little under 5 billion passengers a year, enplanements a year, a little under 50 million flights a year. Again, this is commercial flights. With this kind of demand in the system, of course, that's resulted in the pain increasing as well. So domestic U.S. delays are now estimated to cost about $30 to $40 billion, primarily in terms of direct operating costs to the airlines themselves. On the passenger side, the pain of delays globally are estimated to be about $60 billion a year. But there's also a significant impact in terms of the environmental impact. So, delays resulted in an increase in pollution. They also cause waste in jet fuel. Now, in a system that's already pretty close to capacity, and we'll talk a little bit about the causes of congestion and capacity in the system, there's a growth that's expected as well. And there are two sort of trends when we think about what the next generation of air transportation systems are going to look like. It is clear that there's going to be an increase in the level of autonomy and the level of automation. And the autonomy comes from something that, even in the past 5 or 6 years has become, commoditized to the point where you can walk into a department store or a Target and buy a drone. So there's autonomy on board the aircraft themselves, and there's also automation, and by which I mean decision support either for pilots or air traffic controllers who are managing traffic. And sort of two trends in this, I mentioned drones earlier, but there's also proposals in terms of urban air mobility, which would be imagine rideshare, but for air travel. So in busy areas like like parts of California, the LA area, or Sao Paulo is a place where there's an increased demand. There's so much congestion on the grounds that you would like to actually move to the third dimension and be able to fly autonomously. So in this system, I'm going to talk about my research, and my research broadly over the past little more than a decade has been around building algorithms for air transportation, and I say practical algorithms for air transportation, where the goals of the objectives of these algorithms are typically to improve system performance. And this could be in terms of efficiency, it could be in terms of robustness, where you don't want something, disruption in one part of the system to quickly cascade and spread throughout the entire system. And you would like to maintain the high levels of safety that we've come to expect of commercial air travel. And in my opinion, the reason why it's hard to achieve these objectives in practice is three things to simplify matters. The first is there is a lot of uncertainty, and I'm going to talk about this because the fundamental reason for things like delays is that weather is hard to forecast. There's uncertainty over, even the capacity of the system at any time. The human operators, so we still do have a situation where even as the aircraft are getting higher and higher levels of automation, there are human operators and human stakeholders in this, and their decision making it comes into play as well. And then the third is that it's the commercial air travel system, and certainly as the demand is being driven by entities like airlines who are competing with each other, and different stakeholders in the system are competing with each other. Our approach to overcome these challenges is sort of threefold. The first is we have an increasing amount of real-world operational data that we would like to leverage in order to, improve the functioning of the system. The way we use this data is to build simple interpretable models. And what I mean by interpretable models is models which can help us inform to better help decision makers make better decisions, and to convince them that the system is doing the thing, the algorithms are doing what you would expect. So you'd like to be able to explain what the algorithms are doing. And ultimately, because we expect an increase in demand, we want to use these models to develop and implement scalable algorithms, and in particular algorithms for controlling, so regulating the system behavior and optimizing the system as well. And ultimately, I do believe that we are going to need this sort of practical algorithms and decision support in order to, improve future system performance. And this goes to where a lot of these transportation systems are moving, and in fact, smart systems are moving, where we have cyber elements that need to come together with the physical elements like the aircraft or the other physical elements of the system, and the human decision makers as well. I'm going to be talking about this sort of philosophy with two examples today, both to do with delays. The first is really trying to understand the dynamics of delay from data. So in this, we're going to come up with models of delay propagation in networks, so explaining how delays propagate in air traffic networks. And in particular, these are going to be networks with switching topologies that I will talk about. And the second has to do with the mitigating the impacts of these delays. So, and this is going to be very large-scale optimization algorithms for a problem known as air traffic flow management. To begin with the first one, this is a movie, so I'm going to have a few of these movies on visualizing flight delays. So the NAS is jargon for National Airspace System. So imagine it's the entire air traffic system of the US. And this is a playback of data. I'm going to pause and set it up. So, so the gray aircraft, so you're going to see, pause for a second. Okay. The gray icons are aircraft. They're not to scale, so they're significantly expanded. This is a day in 2005 when there was weather primarily around Chicago in the morning. So that's around the Midwest here. And as the day progresses, a few of these gray icons, some of them are going to turn yellow when they've been delayed by at least 15 minutes. And when they've been delayed by more than an hour, they're going to start turning red. And again, I'd remind you that it's a day when there's weather primarily in Chicago in the morning. So as you can see that most of the delays start being around Chicago. So all the yellow aircraft are, coming out of Chicago initially. And then some of them turn red. But then as the day progresses, you start seeing flights that are between Seattle and San Francisco, or San Francisco and Salt Lake City being delayed by 60 minutes or an hour. And fundamentally, the issue here is, of course, that aircraft don't stay in Chicago. So if your flight from Chicago to Seattle is delayed by an hour and 15 minutes, then there might be some recovery built into the schedule, but then it's going to mean that the aircraft that aircraft doesn't stay in Seattle. It might be going from Seattle to LA. The crew might be connecting somewhere else, and certainly the passengers might be connecting to a third aircraft. And this sort of visualization doesn't actually include what passenger misconnections are. It only includes which aircraft are likely to be delayed because of that. But this sort of connectivity, the network connectivity of it, also means that local events have very global effects. So the chart on the left is just over a course of a year, so 2016, it shows the number of canceled departures, so canceled flights in the domestic US. Historically, it has been that in these systems, in the air traffic system, what shuts an airport down and causes a large number of cancellations would be these winter storms or severe weather events like a hurricane. Something that we're seeing increasingly often is that it's not something to do with the air traffic system which shuts the airport down. The two biggest incidents in 2016, two of the bigger impact incidents were a computer outage at Southwest and a power outage at Delta, which was caused by a fire in a router room that some people might remember. The Southwest computer outage lasted 45 minutes. The Delta power outage was a little more than an hour. They had an impact of something like, $150 and $177 million each. And the reason for this, of course, is this is just showing the impact of the Delta power outage, which was in one router room in Atlanta. But you see that the delays and the cancellations are no longer contained there. And this is just the pictures within the US, but in fact, globally, you have, a few thousand flights canceled because of something that happens for 45 minutes, because your aircraft are no longer in the right place, your passengers are no longer in the right place, and your crews are no longer in the right place. So what this means is that even when we consider things like weather events, and certainly when we consider events like this, we need to be looking at the global impacts, the network system-wide impacts of these disruptions. The other interesting thing is, why is it important to understand how these things spread? Well, things like snowstorms. So when we see here, for example, the spikes when there's a large spike for a snowstorm here, it typically lasts a day because the airline, to some extent, knows it's coming. And so they might shut everything down for a day, but then they also set it up so that the aircraft are in the right place to recover the next day. On the other hand, when the power outages happen or these unexpected outages happen, the impacts last for several days afterwards because they're unexpected, it happens everywhere, and nobody's planned for it. And so it's actually important for the airlines also to understand where it's going to spread if there's a local disruption, either because of something unexpected like a power outage or even when it's weather. So there is a need to look beyond what's happening locally, and it used to be the belief that, what really mattered was what the local situation looked like at certain important places. So in the US system, it used to be, primarily what matters is what the weather is in New York City. But we now find that the weather can look similar even in New York City. But it can have very different impacts depending on what is happening elsewhere. And so this is 4 days where, an airline partner tells us they believe that the weather looks similar in the New York area, and certainly at the airport level in the New York area airports. But then when we look at what happens in the rest of the system, the maps there are just showing, delays on different origin-destination pairs, so between different airports. And we see that, there are days when, there are very, very high delays everywhere, and then there are days where very little is happening elsewhere. So there's a couple of other factors that we need to look at. One of the things is it really does matter on what is happening elsewhere in the system. So a day when there's bad weather in New York, but then there's also bad weather in, Fort Worth or Houston, or bad weather in parts of Chicago, is going to be a lot worse than a day when the weather is pretty much bad in New York, but okay everywhere else. And then the other aspect is really the demand. So this day here, September 6, 2014, is the Saturday after Labor Day, and there's not very much travel going on. So you can have terrible weather, but if you're going to have terrible weather, the right day to have terrible weather is a day when not much flying is going on, because you can still manage. But certainly it motivates the idea that in order to give guidance to airlines on how the system is performing, and even to the system operator on how the system is doing, you need to be looking at the connectivity and the network impact of these disruptions. And of course, I need not mention it here, but networks are ubiquitous, right? So we've developed techniques to model networks. We've developed techniques to model propagation on networks, and this has been used in a huge range of contexts, from power grids and communication systems and public transport, even other forms of transport systems, and even propagation in terms of epidemics. It's been studied, including by several people in this room. There are some assumptions that are typically made to improve the tractability of these network problems, especially when it comes to things like propagation in these networks. The first is you typically assume that the nodal state, so the state of a node, belongs to a small set of discrete values. So, for example, you might have a node it's a population that's susceptible to a disease, it's been infected or it has recovered, right? So these are the standard SIR models of disease, epidemic propagation. You typically assume in these networks that the interactions between two nodes in your network are unweighted and undirected. So in other words, you either interact or you don't. Two cities either have some relationship between them or they don't. And that if city A influences city B in one way, then the city B influences city A in exactly the same way. And the third assumption that's made is that the structure of the network itself, those interactions, the connectivity, is static with time. There are some things that are different because part of what we want to do is we want to see if find models from data that can accurately or reasonably reflect the behavior of the actual system. And with air traffic delay networks, we find that there are some things that we care about, that are special about these networks. The first is it's not true that an airport is either delayed or it's not, right? So the level of delay at an airport might be 5 minutes, it might be 15 minutes, it might be an hour, it might be 2 hours. And I really do care about, where on that scale of that continuous scale we are. The second is that the interactions between cities are very much weighted and directed. So certainly the relationship between Hartford and Boston is very different from the relationship between Boston and Hartford in terms of how delays in one are going to impact the other. And the third is that because there's so much variability and seasonality with regard to the demand. So there are certain hours of the day when there's going to be high demand in certain airports, as well as the capacity, because weather phenomena like wind direction and visibility, fog sets in at certain hours at certain airports, and so on. So the networks are very much time varying when we think about their, what they're going to look like at different periods in time. So we're going to try to build models and use those models for analysis. Network models that will reflect these things, these characteristics that we really do care about. So one way we do this, so the network-centric view of air traffic delays that we come up with, one could be that our network is going to represent the delay at any hour of the day, right? So I'm going to take a snapshot of my system, and my nodes are going to be the airports, and the weights on each of my edges is going to be the level of delay. So this could be the median delay that I see on flights that are going from one airport to another at some time. And this is something that if I take a snapshot is going to be a weighted directed network. So this is a small example of that where I could have during this hour flights from, I'll use these 3-letter codes that I don't expect everybody to be familiar with, but ORD is Chicago O'Hare. So it could mean that flights from Chicago O'Hare to Atlanta are being delayed by 20 minutes, but then there are no delays on flights from Atlanta to Chicago. On the other hand, flights from Dallas-Fort Worth to Atlanta being delayed by 5 minutes, whereas flights from Atlanta to Dallas-Fort Worth are only being delayed by a minute and so on. But if I have a data set with what the delays on any flight is in any hour over, let's say, a 1-year period or 2-year period, for every hour of that time period, I can come up with an adjacency matrix that represents what that network looks like. Now, if I have an adjacency matrix that's static, we can actually come up with a very simplified model for how the delays are likely to propagate under that connectivity. So one idea would be that if the states I care about are the inbound delay, so how much delay is coming into an airport and how much delay is going out of an airport, then given this adjacency matrix, I can come up with the following representation, which is, firstly, if I think about the delay at the next hour, so DI at airport I, so which is the delay that's coming in at an airport I in the next hour, well, there's going to be two components. The first is that if I already had delay building up and congestion building up, it's not going to disappear. So there's going to be some persistence, which is because of the way the airport works, the queues build up. And so we have one term, which is going to be this alpha I in times that delay in the previous hour, Plus, there's new flights that are coming in which are delayed that are going to be fed in, and that's going to depend on this adjacency matrix. And then similarly for outbound delays, I'm going to have some persistence, and then I'm going to have some flights that are going out that are delayed, which are going to contribute to the inbound delays at the other airports. So essentially, I can use this, once you give me the data, to come up with a model, a linear model, where I have an interpretation on the different terms on what the persistence of delays is and what the network effect, how susceptible are you to delays in other places. And then from this, we can come up with the state of the system, which is just going to be a long vector with all the inbound delays and all the outbound delays and all the airports. And then if I have this fixed network topology where the adjacency matrix is constant, the system is going to, I can write a linear dynamical system model for how the delays propagate. In particular, it's going to depend on this calligraphic A matrix, which is going to be symmetric even if my original topology is weighted and directed and therefore not symmetric. So now the issue is this, which is if I have a fixed network and you ask me how do delays propagate, well, I can answer that question. But I started by saying that, well, the network doesn't look the same. The network changes from time step to time step. And so that it can take any set of values, right? Which makes tractability impossible, because what am I going to say with, oh, it can be anything at all. So the next question we can ask is, if you give me two different snapshots at two different times of this network, how do I tell whether they're similar or different? So this is a question of trying to decide some sort of similarity in how these adjacency matrices look. And there's a couple of ways we can do this. The first is to actually look at the dynamics, right? So the dependence on the delay, evolution of delays is on this calligraphic A matrix. And so to some extent, we know that the principal eigenvector of A forms an invariant subspace where once we're there, we know that it's going to sort of stay there. And so if you give me two different adjacency matrices, I could look at the eigenvector of the matrices and say, are they close or are they far away? There's an alternative, which is go to network theory and look at like some sort of centrality metrics. The centrality metrics, you can't use something as like eigencentrality because that only works when you have, undirected graphs, because, you want your eigenvectors to be real. However, there is an extension of eigencentrality, so the centrality metrics, to directed networks. And this comes from Kleinberg in the 1990s with regard to web pages, where you can say that every node no longer only has a connectivity metric, it has two forms of connectivity. It could be pointing to things, or there's nodes, other nodes that are pointing to it. In our case, you're either sending out delays to other nodes which are getting a lot of delay, or you're getting sent a lot of delay from other airports. So the notion of these hub and authority scores is a strong hub, which is an airport, will be one which points to a set of other airports which are called strong authorities. It's a cyclical definition. A strong authority is one which is getting pointed to by a lot of strong hubs. Now, in terms of computation, it turns out that Benzi and others in 2013 showed that the hub and authority scores in a network, in a directed network, can be computed as the principal eigenvector of that same A matrix. So this is good for us because it says that whether I'm looking at the dynamics or I'm looking at the sort of just network effect, I'm going to end up with the same characteristic thing that really matters, namely the eigenvector of this, the hub and authority scores. So what this now means is if you give me, let's say, a few thousand possible snapshots of these networks, and I want to group them, so I want to cluster them in some way into different networks that look similar, I can do that by coming up with a set of feature vectors. And the feature vectors that we pick are in particular going to not only look at the instantaneous inbound and outbound delays at each airport, but also the network effects in terms of these hub and authority scores. And you can also look at the first derivative in terms of are the delays increasing or decreasing. So this is a very simplistic model because this is going, if you have a network with n nodes, the adjacency matrix will be order of n squared, but this feature vector is going to be order of n, right? Because you're just going to have two scores for each node. When we do this, this is using about, let's say, a year of data is what we first do this with. We can then figure out, there's work that you need to do using, various criteria on how many clusters to pick. But it turns out that each mode, right? So you now have the system where I'm saying there are about 12 characteristic topologies that tend to repeat themselves, and any other network I can say falls into one of these. We can qualitatively label them based on where things are bad, and it kind of makes sense from the domain expertise point of view as well. So there is one sort of mode where San Francisco has delays. There is a mode when everybody is in trouble. There's one where Atlanta is, seeing delays. O'Hare is seeing delays. There's one where there's moderate influence everywhere, and there's one which is really low NAS, so there's not much high delays anywhere, and this keeps happening every night, right? So typically the system overnight goes to a period where there's not much delays. But what it then allows us to do is to actually use this to write the full model. So what we're going to have now is we've identified from the data a set of characteristic topologies, right? So this is like the modes of our hybrid system. So we're going to have these discrete modes of operation. So at any hour, we're going to be in one of these topologies. Now, we can also, once you tell me that these are all the periods of this topology, I can identify those alpha and beta parameters. So I can identify the linear dynamics of the topology from, under that topology from the data. But what is happening, in fact, in the system is the system doesn't stay there. The system keeps jumping, right, between these different topologies. We're going to assume, that the system switches randomly. So we have a switch linear system with Markovian jumps. We can learn the Markovian transition matrices again from the data. And we're going to end up with a class of systems called a Markov jump linear system. For those who are really in this space, in fact, we're going to get a positive Markov jump linear system because delays are only going to be positive. Delays are going to be non-negative, right? So we end up with models like this where, your state vector is going to, under a given network, is going to evolve in a particular way. That gamma is going to depend on all those alphas and betas and the calligraphic A matrix from earlier. And then at any time, we have a probability, which here I've written as it's a constant probability, but in fact, we will relax this to be pi ij at time t, which is going to be the probability that at the next time step, we're going to move to a different mode or, the same mode. And then we can even have, in some cases, when the mode transitions happen, the continuous state can also jump, and we can have these resets, but we can actually identify all of this from data. Okay, so far we have a way of identifying a model. There's two things that we want to do with these models. The first is going to be, we would like to see, these models are going to be tractable to analysis. So we want to build analysis techniques for these models. And then we want to validate these models to make sure that they're actually reasonable representations of what the system is doing. So with
So what's the T here? How much?
An hour is what we usually use, that every hour of the day, it keeps transitioning. So there's a physical interpretation of stability, which is over time, right? We know that the delays actually do decrease, right? Because the demand goes and it decreases. So part of the stability analysis is just a sanity check on do you actually, do delays decay. There are different notions because it's, these are stochastic models. We're going to have to look at stochastic notions of stability. So you can talk about mean stability or almost shear stability. So it's just a question of, do you just looking at the expected state going to zero or as time tends to infinity, or do you mean that every realization should go to zero? But what we've done is we have these discrete time Markov jump linear systems, but we also have time varying transition matrices. And in particular, in our case, those transition matrices, because there's such strong time of day impacts, they're actually going to be periodic, right? With every 24 hours, you're going to have a sort of repeat in your transition matrices. So we want to be able to analyze these. And we've come up with conditions. And the first thing we can ask is, what does it even mean when you think about stability of a Markov jump linear system model? So the first question, if you've done a linear systems class, is it enough if all my modes are stable, right? So if each of my individual models is stable. It's a pretty classic result there's two sets of things we can lean on. One is if we actually plot the the spectral radius of each of those models, we find that some of the modes are unstable and some are not. In particular, the increasing delay modes are not going to be stable because they're increasing delay. But it's also well known that the stability of these individual modes is neither necessary nor sufficient for the stability of the switch system. But then more interestingly, we find that if all I do is to take an entire years worth of data and calculate what the average transition matrix is empirically, we find that it's actually the system is not mean stable, which is not physically seen, right? We know that the system is stable. So one of the things we then notice is that, as I mentioned earlier, those transition matrices vary a lot during the day. So this is just a visualization of the transition matrix over the course of 24 hours. Again, learned from the data. It renders a little weird, but then you can see that there's a strong temporal thing where the matrix doesn't look the same, right? The matrix does actually vary because there are periods of time when certain weather events cause delays to start, and then those things stay for a while, and then towards the end of the day, things start dying down again. And then we can show, in fact, that once we have this time-varying transition matrices, the system is both mean and almost surely stable. The interesting thing for us from the point of view of the control perspective and as engineers is that this also means that the system is actually being stabilized by these transitions. By more transitions, which then sort of leads to some follow-on work, which we're doing right now, which is on optimal control, where we can ask if I can actually find the way to trigger these transitions, if I can tell what the FAA needs to do or what the airline needs to do in order to transition from one of these modes to the other, how do I quickly recover from, the onset of delays? So that's sort of the analysis question. The other I said was, of course, we want to know how good a representation of the system is. This is. And so for this, what we can do is we learn the model from using data from 2011. We then validate it using 2012, where we predict what's going to happen. And then we try to see if we can actually represent and predict how the system is going to evolve. So the plot on the left is just showing the total system delay. So this is system-wide everywhere. The middle line is the mean, and then the bars are the variability, showing the how much it varies. Because one day you can start at sort of similar points, on a bunch of days, but there's slight variability in the starting conditions, and then there's certainly variability on these transitions, and you have a stochastic model. But overall, we see that it does actually capture reasonably well the trend in delays. We don't do such a great job in the end because, well, it turns out that 12 modes is very, very few modes to represent, many, many different topologies. So we don't have enough decreasing delay modes to accurately represent it. And so there's things that we can do to improve the modeling. But overall, we're actually pretty happy because it captures the delay trends reasonably well as the variability we see. And then including at individual airports. So you can show that you can at any time, if you want to know, a few hours ahead, what is the delay level at an airport, the state of the system you can predict to within, 8 minutes mean error, what the delay at an airport is going to be. So what are we doing with these sort of models? We've done some analysis and validation. So there's a whole lot of extensions that we're now looking at with this. So the first is analysis. So the stability that we looked at was asymptotic stability. So eventually it'll go down to zero. We also do care about how fast it goes down to zero. So we can ask questions on, we have some results on the finite time stability of these systems. More broadly, we are now interested in just conceptually in these network systems where you have these models. It's really hard to come up with accurate models. Even though in this particular case we came up with a good model, a lot of these sort of systems which show up in these networks, all you know is the sign of interactions, where I know that airport A influences airport B or node A influences node B positively or negatively. I don't know very much about the magnitude of those interactions. And so now the question we can ask is, if you have networks where you only know the sign of interactions and you have switching between those, can we say something about the stability of these systems? And more generally, we can also ask the question, which we started working on now with my student, Joao Cavalcanti. What can you say about the controllability of these systems? So what is it about these matrices, the structure of these matrices, where we can say something about controllability as well? I mentioned earlier that the recognition that it seems like the system is stabilized by these mode transitions then opens up the engineering question on optimal control of these networks. So if I can influence mode switches, or I can influence, changes even in the continuous state, how do I do, optimal hybrid control of these networks where I can have some level of autonomous switching as well? I mentioned earlier, an important aspect of this is being able to predict how delays are going to evolve. And so there's some work that we've done in using the current delay state, which might be the adjacency matrix at this time, to predict what the delays are going to be a few hours from now. And then, it gives us a way to generalize to much more complex networks where we could have multi-layer, multi-timescale networks where, you have one layer which has to do with the cancellations, one layer which has to do with traffic demand, one layer which has to do with capacities, and see how these interact. And then more broadly, use similar methodology to look at interactions between different types of networks as well. Sort of my favorite example of this is when there were snowstorms a few years ago in Atlanta. Atlanta has been seeing an increasing number of snowstorms over the past few years, so they've actually invested in snow removal equipment. Storm sets in around 8 a.m., and by 11 a.m., this is the airport. It looks great because they've cleared out the runways and everything's good to go. But the problem, of course, was this is what the outside looked like. So some of you might remember this was when there were people who were sleeping, kids sleeping in school buses and cafeterias. But when the road outside looks like that, your crews can't get in, your pilots can't get in, your passengers can't get in, and then you end up canceling 3,000 flights, even though, you've cleared out your runway. So there's a broader question on using these methodologies to build, the network of multiple interacting networks so that we can understand how impacts propagate from one network to another. So that's sort of the thing on the first piece on just coming up with data-driven models to understand the how of and why of how delays propagate. The next piece is what can we do about it? And this has to do with mitigating the sort of impact of these delays, and it's an optimization problem. So to understand what causes these delays, to understand how to solve these delays, we have to understand what causes them. And the biggest cause is, again, capacity impacts. So let me pause for a second. So this is going to be a playback of flight tracks on a day when there's weather. And this is a day we pick when the weather is pretty much in the New York, Philadelphia area. Each of the red dots is an aircraft, and the white line is the position, the 5-minute history of its track. And the green, yellow, and red cells are thunderstorm cells. So as the storm moves in from the north and the airspace gets blocked off by thunderstorm cells, we're going to start finding that flights are going to deviate, and you start seeing holding patterns coming in. And, it doesn't take a long time before you start seeing holding patterns over the Midwest, right? And then the storm moves south and you start seeing holding patterns over, Florida and Georgia for weather that's pretty much isolated in the New York area. And of course, the reason this works now, this happens currently in the system is there's very little proactive planning. So you pretty much wait till the storm closes down your access to New York, let's say, Newark Airport, before that controller says, I can't take any more aircraft. And so you now have refuse is a strong word. They can't accept any more aircraft. And so that means that the airspace immediately surrounding New York has a lot of aircraft that are going to be put on hold. So that controller is at capacity. So they say, I can't accept any more aircraft, and so this starts cascading down. And of course, once you have congestion that's built up somewhere here, you could even have a case where aircraft are going from airport A to airport B, neither of which is New York, but you can't use the airspace that you need to use, and so you're going to see delays as well. So this problem of how do you manage the sort of capacity constraint strategically is really what is called air traffic flow management. And the idea is the following. The basic idea is that congestion leads to delays, and congestion happens when you have an imbalance between capacity and demand. And that can happen either because you have reduced capacity, let's say because of bad weather, like the case we saw, or it could be because you have really high demand, because, peak hours, or, it's a holiday season and so on. And these delays have significant economic impact, both in the US and in Europe. It's known that, the delays have an economic impact. So the idea behind air traffic flow management is that you can, if you know that there's bad weather coming in some place, you can more strategically allocate your resources both in the airspace and the airport in order to mitigate this impact and not have the sort of widespread spread of delays, and not have airborne delays, and instead, try to incur as much as you can on the ground. And of course, we already have capacity constraints today, and as I mentioned earlier, we do expect to see an increase in demand, both in terms of commercial air carrier operations, as well as in terms of unmanned aircraft and on-demand mobility services, as I mentioned earlier. So the fundamental capacity constraints here, if we think about what drives the capacity of an airport or the airspace, there's different ways in which these are represented. So airport capacity is typically represented in terms of these, what are called capacity envelopes, where it tells you what the trade-off is between arrivals and departures at that airport. So if I have a lot more landings, I'm going to be able to have fewer takeoffs because I'm using most of my limited capacity of the airport for arrivals. And then because your separation requirements vary depending on the visibility, depending on whether it's good weather or bad weather, you can actually have very different envelopes on what capacity, how many aircraft can take off or land in some time period, let's say an hour or 15 minutes, right? On the airspace side, it's a little more complex. The airspace is divided into sectors, which are managed by 1 to 2 air traffic controllers, and their responsibility is maintaining separation primarily. But if you ask the question of how many aircraft can be in some region of airspace, it really depends on the geometry, the shape of the airspace. It depends on, whether all the traffic is going parallel to each other along the same route, or there's a lot of intersections that need to be managed. It depends on the workload of the controllers. It depends on the weather. If you have large thunderstorms sitting over parts of the airspace, you may not be able to use all of it, and so on. But there's typically, of the order of 1,000 sectors, or, depending on which are on different altitudes, you can have up to a couple of 1,000 sectors in the airspace. So what we want to do primarily is we want to mitigate delays, avoid delays, but then we want to allocate resources, and the capacity of those resources are typically given by these airport capacity envelopes or some sort of numbers on how many aircraft can be in the airspace at any time. So there's now going to be an optimization problem, and what makes this optimization? So we're going to say, well, there's a lot of aircraft, so it's going to be a hard optimization problem. There's a couple of things that make it particularly difficult, like even harder than just the number of aircraft. The first is that connectivity that I showed in the first video, where aircraft don't stay where they are. In the US, only about 6% of flights fly one flight and then don't do anything else. So most of them continue on. And in fact, the median number of flights a day in the US is, somewhere between 4 and 6, right? There are aircraft that do 12 flights a day, where they're going back and forth between 2 airports, let's say. Of course, we saw in the first part of the talk that this results in delay propagation. The other issue is going to be that it makes any sort of rolling horizon optimization, where I say, I'm going to only optimize for the next 2 hours. That's going to be very suboptimal, because if I decide to delay a flight heavily, or I decide to cancel a flight because it's optimal right now, I may not realize that flight is doing 4 other flights, and now it's not in the right place. So I'm going to end up canceling those 4 other flights. And both in US and Europe, this is just looking at causes of delays. About 40% of all flight delays are caused because the previous aircraft showed up late, right? That connectivity effect is very, very strong. The second thing, of course, is things change. In particular, those capacity envelopes that I showed, it depends on the weather. The weather can change. So I want to come up with optimization methods that are amenable to stochastic implementations, or at least amenable to very quick solving as conditions change. I'm not going to have time to go into a whole lot of detail on what we're going to do, but if you think about the technology that's going to allow us to solve the sort of massive optimization problem, we're going to use the 4D trajectory. So we're going to use the trajectory of an aircraft in both space and time as the construct over which we're going to allocate these airport and airspace resources. And what that does is it sort of defines the path of the aircraft. And currently where this is used typically is it's used to avoid collisions, right? If you want to know whether tactically, whether two flights are going to be too close to each other, you're going to look at those trajectories and see whether they're too close, and if they are, you're going to come up with deconfliction. But what we recognize is that the moment you tell me where that flight is going to be, I have to some extent I have an expectation of which resources it's going to be using at any time. So we could be using the trajectories for air traffic flow management as well, which is what we're going to be doing. And the other advantage of this is everybody has a trajectory, whether you're manned or you're unmanned or you're on demand. So you can use that to represent everybody's resources in some way. So the air traffic flow management problem is actually pretty simple. The first mathematical formulation of this was by my colleague, Professor Amedeo Odoni, in 1987 as a large-scale optimization problem. And the idea is the following, which is I have a set of flights that I would like to fly, right? I know which flights I have to fly. I know which aircraft are flying each of these flights, and I have some expectation of what the capacity of all my resources are going to be. I want to find an optimal trajectory for each of these aircraft such that I maximize a system-wide benefit and then satisfy a bunch of operational constraints. These operational constraints are going to include our capacity constraints that I talked about earlier, but they're also going to include things like what my flight connectivity is and the minimum turnaround time, where I need enough time for passengers to get out and, to clean my aircraft and to get ready the new passengers on for my next flight and so on. And then laws of physics, right? There's only so much fuel I have, so there might be a maximum amount of delay I can take, and then there's going to be a minimum amount of time I'm going to take because I have a finite speed as well. And there's not a whole lot we can do in terms of the control or the decision variables. The control actions we can take are forms of delay. We can delay aircraft on the ground. We can delay aircraft in the air by flying slower. We can sort of transfer delay by having them fly a different path, and we can delay them so much that they get canceled, right? And so the idea is going to be to sort of solve this optimization problem for a large number of aircraft. I want to leave a few minutes for questions, so I'm going to skip through where this is and we'll come back to this. But what we're going to do fundamentally to answer this is we're going to think about trajectories. We're going to think about trajectories where we're going to solve this in discrete time. So we're going to discretize time. We can pick 5 minutes, and in the experiments that I'll show, we pick 1 minute intervals. So we're going to discretize the trajectory. So every minute, we're going to have some understanding of where in space and time that flight is going to be, each flight is going to be. And the path of an aircraft, the trajectory of an aircraft would be represented on a combination of nodes and times, where we might say you are supposed to leave the gate at your origin airport at some time. You might decide to stay there for an extra amount of time. You then move with some transit time to the runway. You then have some runway capacity, but might have to be satisfied here. You then move to your departure fix, and then there's like different nodes that you pass through. And then nodes are going to be, also there's an assumption that certain nodes are going to belong to certain airspace sectors where we're going to be imposing capacity constraints, and then you get to your destination all the way. So the mathematical formulation of this is, I'm going to just talk about, we're going to start by looking at the deterministic case. And let's talk about the interpretation of this, where what we want to do basically is we want to maximize the benefit, the total benefit, or minimize the total cost of the trajectories that we're going to choose for all our aircraft, such that every aircraft only gets one trajectory, right? It can only fly one path. We're going to satisfy all our sector capacity constraints. We're going to satisfy all the airport capacity envelope constraints. And since there are many different trajectories that I could have for every aircraft, I'm going to say, here's the trajectory that I'm going to pick. So it's just saying this. Broadly speaking, what we're going to end up with, I'm happy to give access, this paper's on my website. You can find the gory details. It's going to be a very large-scale integer program. We're going to solve this using an LP relaxation, so column generation or dual decomposition. But the idea here is what we're able to show is that the sub-problems we can solve firstly, independently for each aircraft, so which is called the tail in, again, air traffic jargon. But that subproblem is a longest path problem on a directed acyclic graph, and we can solve that very quickly and efficiently using dynamic programming. And this also allows us to distribute the computation as well, and we can have proposed effective heuristics to obtain bounds to show that we're actually close to optimal, to assess the optimality gap. The more interesting thing is actually the physical interpretation of what this solution process does, which is what it does is when we start, there's a sort of every airline or every aircraft operator says, here's what I'd like to fly. We have so those are the initial flight plans. We have the capacity forecast that we think, and we have the set of constraints that we need to satisfy. What the centralized master node, who is a system operator, might do is to see if it's feasible. You can always come up with a feasible solution by canceling, a very large number of flights. It's going to be an expensive solution, but it's going to be a feasible solution. We're going to use that to generate prices, right? Certain resources are more congested than others because more aircraft want to use it at the same time. We're going to publish those prices, and each airline or aircraft operator is can on its own take those prices, decide whether it can fly a better trajectory at those prices or not, and then it publishes just those new trajectories and those valuations, right? So it's entirely distributed. Each airline is making its decision on its own for what's best for itself. And then the node, again, the master node looks at other new trajectories. If yes, it then repeats this and then recomputes the prices and publishes. And then we do this till we get to optimal. What this has allowed us to do is, yes, there's a nice interpretation here on distributing the decision making and allowing autonomy for each of the aircraft operators. But it's also allowed us to now scale to problems which are 5 orders of magnitude bigger than things that were dealt with before, and I'll show what this looks like. We've parallelized, so the implementation that we have is on a 40-core machine on the Amazon cloud. We solve a 24-hour horizon with 1 minute trajectory discretization in about 4 minutes, right? And so you can keep doing this. I also wanted to sort of mention one thing on the whole, the autonomy side, because I said that there's an increase in autonomy, and I know a lot of people who have interest in autonomy here, and I mentioned here that the demand is a combination of manned and unmanned aircraft. So here's a New York Times headline on a robot-piloted plane makes a safe crossing of the Atlantic. Supposedly a flight from Canada to England, fully automatic flight. When do we think this happened? Or has it happened yet? Could have made up a fake headline, right? So you can probably tell from the nature of it, right? So 1947. So we've known how to fly one aircraft autonomously for quite a while. There are lots of remarkable things about this flight. One is there were actually some 14 civilian observers, including reporters. So the fact that people were willing to entrust their lives to an autonomous aircraft is pretty remarkable. Also, the fact that these actually predicted both drone warfare and Amazon Prime Air, saying that in times of peace you would be used as cargo carriers. But this also shows that the difficulty of it is not so much controlling one aircraft, it's really the integration with everything else that's happening in the system, right? That's where the challenge is. And that's really where this, like doing this in large scale, is like scaling it to be, to use the word of the day, is really the challenge. So where we've sort of tried to go with this as part of an SBIR with the startup, Lumo that Sridhar mentioned, is look at a projected data set, both in terms of manned and unmanned aircraft. So 48,000 flights within the US manned aircraft, and then a large unmanned data set at a range of altitudes. And then various combinations of costs and capacities. You can do things like geofencing. And we actually have this accessible by API where people can, in fact, Metron, which is a subsidiary of Airbus, worked with us in, testing it out under some weather conditions. But what it allows us to do is to optimize, about 77,000 flights in under 4 minutes. And then if you're doing a rolling horizon mode, because anytime new demand comes in, you can reprogram and you can do, 6 to 8 hour rolling horizon in under a minute. Okay. So now that the skies are busy enough, the red aircraft are unmanned aircraft, the blue aircraft are manned aircraft. There's a fair amount of, in this data set, they expect that there's going to be fish aquaculture surveillance happening, which is why there's a fair amount of traffic off the East Coast. That's a pretty crowded sky, but you can very quickly optimize this and then do things with regard to, blocking off certain regions of airspace and everything else using just those pricing signals, right? And you can do it very, very quickly. So to wrap up sort of with this, where, as I said earlier, there are now a whole lot of open challenges that we can ask, which have, we can solve the optimization problem, but we can be asking questions at a higher level on how do you look at fairness in this? How, what is equity when you have multiple constrained resources? Right now in the air traffic world, first come, first serve is equitable. But if you have multiple constraints that you hit, it is obvious that if you do first come, first serve in every resource, you're going to be extremely inefficient. So how do you look at fairness in this? How do you look at incentives for them to participate and for airlines to report truthfully? And we've been doing some work around this. We have some work around looking at the stochastic variant with scenario trees and predicting it. Although I think part of it is if you can solve it fast enough, anytime anything changes, you just resolve for whoever's left. So that might be the other approach around it. And then there's things you can ask on terms of privacy of both the flight valuations and of flight delay costs. Will the airline share it? There are questions on security, much of, the work on connected vehicles that are happening here. And then ultimately, I think a lot of the open challenges that exist in the system are around interactions, right? It could be interactions between the humans and automation or autonomous systems, between decisions that you make, at a strategic level and a tactical control level. And then, as I mentioned earlier, interactions between different infrastructures as well. So to sort of conclude, I think we have shown that there is a lot of promise for algorithmic techniques to improve system performance, and really you need to be considering the different elements of this, not just the cyber physical elements, but also embrace the human elements. There are lots of other facets that are fascinating for us that I will not talk about. Everything from looking at machine learning for aircraft performance from data to work that we've done on congestion control at airports, and then even modeling human decision processes and so on. So with that, I'd like to end, and I'm happy to talk about any of these or answer any questions on the talk as well. Thank you.
So we have some time for questions. 5 to 10 minutes. So I have one, just not being totally familiar with how this gets implemented. So if you solve this problem, do you get like the master plan to some kind of a centralized node, and they can then distribute it, or are these ATCs fully distributed, or?
Well, so ATC is weird in that it's very hierarchical control.
Okay.
So at this level where, you decide on overall aggregate, it tends to be a little bit centralized on here's a rough rate at which we're going to do various things. But then it's also very distributed, in fact, decentralized in the sense that ultimately the controller in charge of that airspace gets to decide whether they're going to allow another aircraft in or not. And that's its own thing. Which is good because it actually, however, where the tension occurs, right, is between if you make the wrong decisions up ahead or you don't do enough strategically, you're going to hurry up and get here and then hit that, which is what happens right now. If you get over aggressive, then you're going to starve your runway. So I think a lot of it is because all tactical management is very distributed. It's that sweet spot where you tell people which decisions they can make up ahead. That could be centralized. On the other hand, if the centralized decision making requires everything from the airline, it's going to be hard to implement. Or if you have to tell me exactly how many people you have on board your flight and how much it's going to cost you today, that's going to be really hard because they're not going to share that information. There isn't that level of trust. And certainly, so that's very dynamic. So what you want to allow is also that distributed decision making where you're signaling congestion or you're signaling crisis and you're giving good incentives for behavior. But on the other hand, you're giving the stakeholders and the operators the autonomy to make decisions based on their own internal costs. right? So you want to distribute decision making at multiple levels, whereas
Yeah,
there's
sure.
the controllers and also the operators.
So then the follow-up, can you just give us a baseline of what it looks like today? I mean, from this hierarchical picture, is there a a rudimentary master?
So I think you end up seeing, so when you have good weather, things are mostly fine, but then you do have a lot more propagation, right? So today the impact of it would be about 40% of your delays. So about 20% of all flights are delayed by at least 15 minutes. And the largest fraction of them are being delayed because of something that happened in the previous leg.
So is there? So from that perspective, there's too much autonomy at the local level. They just don't take into account the network connectedness.
There is very little pre-planning.
Okay.
Right. It's hard because you don't actually have the forecast and you don't have the ability to make that decision.
Yeah. So one question I have is, how do you validate whether your results of the optimization are actually going to be correct? As in, so you see some weather pattern.
Yeah.
But whatever that particular decision that they did at that particular time, you only have that particular data.
Yeah.
So how do you go about validating some of the algorithms?
Yeah. So there's two different. So you can ask the optimization. You can actually ask the same thing for the modeling itself, right? I showed you a bunch of aggregate things. So you can ask this.
Yeah.
So the validation on both is really hard. On this, one of the things as part of the NASA SBIR was actually to give a tool where if I vary this, how does it change, right? To help set a baseline on if I actually knew what the weather was, what is the best I could have done, so that you can then tell whether I was close or not, right? So it helps with the benchmarking. Where even the modeling, the validation comes in is partly, it is very difficult for someone to look at performance and tell whether it was because of the weather impact or it was because of something else, of my schedule, or it was because of something else happening. So I think a lot of what these things help do is at the first level, they help you benchmark, right? On this day, if I expect it to be worse than that and it was better, can I come up with why, right? So I think a lot of the use is actually in setting what those baselines would be if I had all that information. The validation of the optimization then is typically the way we would generate the routes is the routes that they actually fly. Sure. So we allow arbitrary routing, but the fundamental idea is that you don't end up with something that looks wildly different from what it would look like. You don't have huge amount of rerouting over a space where there's nothing happening. Right? So it's at that level where you expect to see, if I'm geofencing an area by increasing the prices, I should be able to shut off traffic. So it's around, the validation of the optimization is around smaller cases where you zoom in and see whether it's doing what you would expect it to do at that time.
So one way that I thought of validation would be that, so in some sense, this is either you buy into this whole optimization problem as a whole or you don't. Is it possible to carve out a piece of the optimization and say, okay, only flights in the southwest will deploy this whole control mechanism and we'll see how this works out while other areas in the United States do what is currently being done? Do you kind of see a mixture of these two, or?
So I think that's a little bit harder. You could do that, but then they meet at some places, right? So the challenge will be in places where the traffic, if traffic actually stayed, if you had networks that were isolated, that would be a really cool thing to try. I think in terms of things that people are thinking about in various countries with this is there is this notion of performance-based services where you would get access to certain regions of airspace only if you can show that you're capable of doing something, right? And so I think the notion that we've played around with is more, how do you only allow access to certain types of traffic, right? And that you can adjust with the thing, as opposed to how do you allow access to only do this in certain places. We haven't thought through that. I think that's an interesting question because I think the challenge is going to be where the networks.
How do you decompose?
Yeah.
Well, I think in the interest of time, we should thank the speaker again.